So in our last video, we looked at finding the magnitude of the force of the pressured fluid on an inclined plane. And so if we had some wall that was on an angle and we wanted to find the force acting, say, on an area of it, we worked through this a little bit and we found that the reaction force is equal to rho g times the height below the surface of the water of the centroid of the shape times the area. And the beauty is you can look up where this hc would be, or these moments of inertia can be, in tables. That's the magnitude. The question we want to answer now is, where does that force actually act? In other words, where's the location of the force? So I've redrawn part of this thing here, where what we found in our last video was that the force was equal to the height of the centroid below the surface times rho g8. Now what we're going to use is that the sum of the moments has to be equal to 0, and that's going to give us the location of the force. And so you could imagine that we could write a differential moment as a differential force times y, if it's summing moments about this point here at the top. And if we did a little bit of algebra and calc similar to the last video, we'd get the integral over the area of rho g sine theta y squared dA. That's because we dropped that extra y in there. And that's, of course, then just equal to, if you look closely here, rho g sine theta integral y dA. Well, that's what we had on the last page. In other words, that is the reaction force times yr being the distance along the surface at which the reaction force acts. And so we can pull all the constants out again for constant acceleration and incompressible. We get rho g sine theta integral over the area of y squared dA, and that might look familiar too. This is the second moment of inertia. And the beauty is it's tabulated. And so we're going to save ourselves from doing calculus, thankfully. And so if I rearrange this equation a bit, I can solve for the location of the force as measured along the surface, along the angle of the surface, yr, as the integral over the area of y squared dA, that's the second moment of inertia, divided by yc times dA, where yc is the location of the centroid of the shape, and of course I've just botched this whole thing, so bear with me. I'm going to erase that. By dividing these two equations out and solving for yr, you get the second moment of inertia on top, and on the bottom we get yc times the area, where this is the distance along the surface of the centroid of our shape, and this is the area of that wall. So, sorry for the miscue there. Sometimes this happens. Now, that's all well and good, except that that is the location of the force for a shape that takes the whole space. If we have a shape that's been offset, in other words, if we were just, say, looking at this portion, then our derivation wouldn't work because we sum moments up here. Well, actually it would. There's a trick called the parallel axis theorem, parallel axis theorem, which lets us shift this result anywhere we want. And so we would take that moment of inertia again, which you could write, say, as something like IXC, about the centroid, which is where things will be tabulated, over YC times the area, plus YC. Now, what did I just do? What I just did was I replaced this integral of y squared dA with something that you'd find in a table, which is something like the moment of inertia. The problem is that tables always put these things about the centroid. And so IXC, for example, would be the moment of inertia rotating in the x direction about the axis that goes through the centroid. And then we would divide that by YC, the distance along the wall of the centroid. And that tells us the reaction force relative to the plate on this little block. The problem is we want it in terms of y, and so we have to add a YC to get there, courtesy of the parallel axis theorem. The beauty of all of this is that it's tabulated for lots of shapes. So for example, imagine if instead we had some tank that had a door in it, and that door had a hinge acting like so. But if you actually looked at it from the side, this door were a triangle. How the heck would you perform those integrals? Well, thankfully you don't have to, because this triangle is tabulated up here, and so you can just use these two formulas to get there. The other place that all this comes in handy would be for curved surfaces. In other words, what would you do if your tank looked like this? That seems like it'd be a nice hassle, doesn't it? Well, it turns out it's not too bad, because in order for this to be stationary, any planes that you draw through here also have to be stationary. In other words, I could come make two flat surfaces like so. I could find the forces acting on that surface and the forces acting on this surface and add them together, and they would be acting at a location called the centroid. And so you add this downward force and this horizontal force, you probably get a net force that looks something like that, that is acting in that direction. And so with these things, you're armed that if you crack open the book and look at the tables, you can, for any shape, find the forces that are acting on it and where those forces are acting.